Joining Teledyne LeCroy today for our webinar, Identifying PCIe 3.0 Dynamic Equalization Problem. My name is Hillary Lustig, and I am the Marketing Communications Manager for Teledyne LeCroy. For some of you, this may be your first event with us, so I would like to take a minute and introduce our company to you. Founded in 1964 by Walter LeCroy, we are a U.S.-based company headquartered in Chestnut Ridge, New York, where many of our oscilloscopes are designed and manufactured. Our current real-time oscilloscopes range from 40 megahertz to 65 gigahertz, although if you'd attended DesignCon or OFC this year, earlier this year, you would have seen our 100 gigahertz real-time oscilloscope prototype. In August of 2012, our name changed when we were acquired by Teledyne Technologies. Our presenter today is Stephen Mueller. Stephen received his BS in mathematical physics from the State University of New York at Buffalo. His career has been focused in the test and measurement industry, working previously for Agilent, and now as a field applications engineer for Teledyne LeCroy, where he specializes in signal integrity and high-speed serial data analysis testing solutions. Before we begin the presentation, a few housekeeping items. We will be conducting a Q&A session at the end of today's presentation. Please feel free to submit your questions at any time during the live event, but we will save them until the end. Also, this event is being recorded and will be available to view on demand later today. You can either use the same URL in your reminder email, or I will be sending out the URL along with the slide deck in a follow-up email. So thanks again for joining us. We know how valuable your time is. Stephen, I will now turn the presentation over to you.
Okay, thanks everyone for joining us. Today I'm talking about PCIe 3 dynamic equalization, and I think this is an interesting topic because although it's kind of cutting edge and sort of specialized right now, I think this will be a technology that enables a lot of the common standards and protocols to kind of push the limits on serial data rates. So this is this dynamic link equalization is how they've taken PCI Express and pushed it from 5 gig up to 8 gig. So there are a whole set of compliance tests that are associated with this link equalization technology, but this webinar we're going to focus more on kind of the debug and explaining what this whole dynamic equalization process is and showing some examples of places where I've seen products have issues and failures and stuff like that. So let's jump into it here. So moving from Gen 2 to Gen 3 PCI Express, the biggest change is the bit rate, right? So going from 5 gig to 8 gig. And this is really what is pushing the requirement to have this dynamic link equalization. Also, the encoding changed from 8B10B to 128B, 130B. This actually also presents some signal integrity challenges as well, which when combined with the higher speed, definitely lead to some overall system challenges. But of course, that reduces the overhead from 20% down to about 1.5%. So the effective bit rate was almost doubled going to Gen 3, which was the idea. Now the transmission path is actually the same going to Gen 3. So they kept the same connector, which is was really designed for the 2.5 gigabit per second bit rate. So there wasn't a lot of signal integrity concerns kept in mind when that connector was designed. So that's actually one of the biggest challenges now with Gen 3 is dealing with the connector and the generally lossy materials that people are building devices with and pushing the 8 gigabit per second signal through those interconnects. So because of that, going to Gen 3 receiver testing is now required for compliance, where it was informative for Gen 2. And link equalization testing is a new section that's been added as well. So sending the signal through this same interconnect has a number of signal integrity challenges, as I mentioned. So the basic idea here is we have two transceivers that are trying to communicate with each other. And one is typically mounted on a system board, which could be like a motherboard or a server. And the other one we have on an add-in card. So this could be any kind of device. Maybe it's a storage device or a graphics card, or it could be a bridge of some kind. But we have these two ICs trying to communicate with each other, but in between them is all kinds of transmission lines and connectors and vias, and that signal path degrades the signal quality as it travels along that path. So I'm showing a representation of that up here with these eye diagrams. So the signal coming off of the transmitter initially is a nice open eye, very clean, low jitter, low noise signal. And then as it propagates through this transmission path, the eye starts to close, the signal gets degraded. And typically for PCIe 3, at the receiver we have a closed eye. And if you tried to have a receiver sample that closed eye, you'd get a large number of bit errors. So if you have a closed eye, how do we get the system to work? Well, we use equalizers. So you can have an equalizer before the channel or after the channel. So if it comes before, it's called a transmit equalizer, and after would be the receiver equalizer. And I'm just abbreviating these here, and I might use this terminology while I'm talking of TXEQ and RXEQ to mean transmit equalization and receive equalization. So on the transmit side, for PCIe, we're using de-emphasis and pre-shoot. And then on the receive side, there's a continuous time linear equalizer, or CTLE, and a decision feedback equalizer, DFE. And so by using all this equalization, we can get the system to work, even though the channel is quite lossy for these data rates. So I'm going to give a quick example of one type of TXEQ. And typically the RXEQ, it follows the same concept, works a little bit differently, but I'll show the example of the transmit equalization. In both cases, the concept is the channel is distorting the signal by acting like a low-pass filter. So it's attenuating the higher frequency components of the signal. And so what we do with the equalizers is we try to do the inverse. We boost the high frequency content of the signal. And both the TXEQ and RXEQ try to do the same thing, and they just do it in different ways. So here's an example of de-emphasis. So we have a nice clean NRZ signal here. And if we look at our channel model here where we have our TXEQ block, this would basically be the input to that. And the TXEQ is going to actually apply the de-emphasis, and so the output of that would be our de-emphasized signal here. So what de-emphasis does is it takes the first bit after a transition and it leaves that at the nominal amplitude, and then it de-emphasizes or reduces the amplitude of subsequent bits. So and that's true for the positive or the negative transitions here. And that is essentially boosting the high frequency content in the signal here in anticipation of the low pass filtering effects that this channel is going to have. So I have a quick simulation I can show here that it's a good example to show how this concept works. So again, we have our channel model here. The signal on the top left side of the oscilloscope display is coming right off of the transmit equalizer, but before the channel. And then the signal here on the bottom, and also the eye diagram, is after the channel, but before the receiver equalizer. So what we see initially is, right now we have no de-emphasis turned on, so we see a nice clean signal coming from the transmitter, and then we see this degraded signal at the receiver here after it's gone through the channel. You can see the eye is closed down quite a bit. So as I start the simulation, it's going to step up the de-emphasis in steps of ½ dB, and you can see the eye diagram start to open up. What you'll notice is that while the signal at the transmit side starts to look more and more um, degraded here and looks like pretty strange. At the receiver, we see a nice clean signal, nice clean eye. So de-emphasis works very well to counteract the effects of the channel. Again, the receive side works pretty similar as well, with the concept being that it's trying to boost the high frequency content in the signal. So for PCI Express, the transmit equalization is a little bit more complicated. If you look down on the bottom right side of the screen here, where I'm circling with my mouse, you'll see a diagram of a signal, and we can see the de-emphasis on the signal is represented by this VA voltage here. So that's the bit right after the transition, and then we can see the subsequent bits are de-emphasized. So this is the de-emphasis. But there's also this VC over here, which is the pre-shoot. So this is the last bit before the transition. And so there's kind of another knob to tweak here, so it's a little bit more sophisticated TXEQ. It has the de-emphasis and pre-shoot values as well. But if you look at these are actually just, this is what we're measuring on the signal. So this is the actual waveform we're looking at here that the de-emphasis and pre-shoot values correspond to. This is actually implemented in hardware with what we see over here, a 3-tap FIR filter. So it's by setting these 3 taps here that we can actually create the effect on the output waveform that we see as de-emphasis and pre-shoot. So for PCIe, these are typically referred to as cursors, these 3 taps. And the value that these cursors are set to is the cursor coefficients. And so it's by setting specific cursor coefficients here that we actually create the de-emphasis and pre-shoot, which is our transmit equalization. Now, the PCI SIG has taken some different de-emphasis and pre-shoot combinations, and they've put those into what they call presets. So you can see that in this top left table. There's 11 presets, P0 through P11, and each one corresponds to a pair of pre-shoot and de-emphasis values. So for example, you can see P7 here is 3.5 dB pre-shoot and minus 6 dB de-emphasis. So there's 3 different ways that you can talk about essentially the same thing. So whether it's presets, de-emphasis and pre-shoot, or cursors, it's all talking about the transmit equalization settings. So it can get a little confusing if you're new to this to hear kind of all this different terminology. It's basically talking about the same thing. A PCI Express device can actually request presets or cursors. So it has the choice on whether it wants to use the presets or the cursors. Obviously the cursors give you a finer resolution. There's more options on settings to pick. So kind of an overview of the equalization. On the transmit side, we have a 3-tap FIR filter with 3 cursor coefficients that you can set. Those cursors are going to produce the de-emphasis and pre-shoot, and there's groupings of those de-emphasis and pre-shoot combinations that we call presets. And then on the receiver side, we have CTLE, DFE, that can equalize the signal after the channel. And then this is actually all configured at runtime. And the reason that is because when we connect a PCI Express add-in card into a system, the designer of each of those pieces is different. And they didn't know ahead of time what products you were going to connect together. So for example, if you're developing an add-in card, you don't know if your customer is going to plug that add-in card into a small motherboard for PC, or are they going to plug it into some really large server, or maybe there's a cable in between. So you don't know what this channel looks like ahead of time when you're developing this. So all these equalization settings need to be configurable at runtime. So the selection of which preset or which cursors you're using, the tuning of the DFE and the CTLE, all that needs to happen when the customer plugs the 2 pieces together. they need to talk to each other and work out what are the best equalization settings so that they can maintain a high bit error rate at that 8 gigabits per second. And that's where this dynamic equalization concept comes in. That's just the tuning and optimizing of all these equalization settings at runtime. So the way that's done in PCI Express, I have a couple of link training status state machine diagrams here. Basically, when you connect the two pieces together, the add-in card, you plug it into the system, you power it on. It's going to follow through these states that I have circled here. So you have detect, polling, configuration, L0, and then into recovery. And I have all the substates shown on the right side here for recovery. And one of them you'll see is this recovery.equalization. And this is where the link training is done, the dynamic equalization, to adjust those equalization parameters for that specific channel. And so it's in this recovery equalization state that we're going to kind of focus most of this presentation and explaining how that works and some of the common problems we see in there. So inside of recovery equalization, there's 4 different phases here, 4 steps, phase 0 through phase 3, that are used to go through this whole process of tuning these equalizers. And I'll give you a quick overview here, and then I'll kind of go into a little bit more detail on specifically on phase 2 and 3. So in phase 0, it starts out at 2.5 gigabits per second, and a speed change request is sent along with a transmit equalization setting. A preset is sent from the system to the add-in card, and that preset is to be used when the add-in card first goes to 8 gigabit per second. And that's so that they can establish communication with at least a bit error rate of 10 to the minus 4, just so they can start to advertise capabilities and do the training process. So we need some starting point, some starting preset to work with before we can actually adjust and tune those equalizers. So the system provides that to the add-in card. While they're still at 2.5 gig, the add-in card moves to 8 gigabits per second, uses that preset, and they advertise in phase 1 their equalization capabilities. So this full swing and low frequency, that's the hardware capability of that FIR filter. So that's basically the range and the resolution that that filter has. In phase 2, the downstream component is going to adjust the upstream component's transmit equalization settings while adjusting its own receiver equalization settings. And then in phase 3, we have the reverse, where the upstream component adjusts the downstream component's TXEQ while adjusting its own RXEQ. And finally, when we exit out of this recovery equalization, we should have figured out the optimal TXEQ and RXEQ for both devices, and we should have a link with the bit error rate better than 10 to the minus 12. So I'm going to go into a little bit more detail on what happens in phase 2 and phase 3, because I think this is some of the more interesting parts and where we see some a lot of problems with devices where the algorithms and things aren't working quite as they should in this phase 2 and phase 3. And the result of that, if this process isn't working correctly, is ultimately going to get packet errors. You're going to get if you have a high bit error rate, you're going to get packet errors. You're going to get dropped packets, and ultimately the link will retrain at some lower speed. So I've seen quite a few devices where it's supposed to be Gen 3 capable, but you'll see it retraining back to 5 gig because it can't maintain a good bit error rate at 8 gig. So in phase 2, we have the add-in card is going to be requesting different TXEQ settings from the system, and it's going to be tuning its own RXEQ. So I'm going to go through an example of how that works, and we're going to look at some stuff in the protocol and then also in the electrical level. So this is a really interesting process to try to analyze and measure and debug, because you have communication that's happening in the protocol, but it's relating to stuff that should also be happening in the electrical. And so those two levels are very interrelated in this process. So we'll take a look at both views here. So in order to look at the protocol communication going back and forth, we need to use a tool here. So we have our Teledyne LeCroy PCI Express protocol analyzer software we're using to view the protocol information being sent back and forth between the system and add-in card. And I have a snapshot from that displayed right here, and I'm going to go through to help us understand the information that's contained in this view. I'm going to go through some of the main fields here and explain what they mean. So the first thing you want to look at whenever you're looking at one of these protocol analyzer traces is this R over here. This will indicate which direction the packet is being sent. So the R stands for root complex, and the arrow tells you which direction the packet is moving relative to the root complex. As an aside, there's a lot of terminology, several different names that you can call these two pieces. So this system, which would in practice be like a server or a motherboard typically, this can be also called a root complex or the upstream component. And then on the other side we have the endpoint or add-in card or downstream component. So I use all those terms interchangeably. So this R here tells us we have a message coming from the add-in card to the system. The next section here that's really important for our purposes here is this EQ control. So this tells us, orients us inside of the recovery equalization state, and then also tells us what's going on inside of there. So with any of the sections in this display, you can hover your mouse over it, and the software will give you more information about what information is contained there. So if we hover over here, you get this box, and it tells you EQ control phase 2. So this first number here, 2, that indicates what phase we're in the recovery equalization process. You also see here this TX preset. So we can see preset 7. So that's telling us we have preset 7 indicated here. That's the third number here is the preset. But then you'll see the last field here, use preset no. So we're actually not using this preset, but instead we're going to use cursors here. So in phase 2, I'll remind you what happens in phase 2. The add-in card is going to request different transmit equalization settings from the system. The system is going to respond, and then the add-in card is also going to tune its receive equalizer. So we're in phase 2 here. The add-in card sends a request not for a preset, but for a cursor. And it's requesting specific cursor coefficients here, 6, precursor 6, cursor 16, and post-cursor 2. So it's telling the system, physically set your FIR filter in your TXEQ with these specific coefficients here. And these are corresponding to the TXEQ block of the system. So we can read all that from this packet here from our protocol analyzer trace. So again, kind of summarizing what's happening here. Add-in card requesting a certain cursor coefficient setting in the system's TXEQ. If we look here at the next packet, you'll see now we have a message coming from the system to the add-in card. Again, we're in phase 2, and you can see the system is now responding back and confirming that it has changed its transmit equalization to the cursor settings that were requested by the add-in card, so 6, 16, 2. So we had the request, and now we have the response confirming that it has changed. But it's not just, this is the protocol confirmation, but it also has to have actually changed electrically. So these cursors here are corresponding to a filter here, which is actually the physical filter that's in the system. So if you look at the electrical view now as well, we'll see what that should look like. So the output from the system, we have some nice clean eye diagram. but we want to apply some equalization filter to it, and we want to apply the specific filter that was requested from the add-in card. So the system will set these coefficients into its filter, and the output of that TXEQ block will now look something like this. So it's a fairly distorted signal here, but that's a good thing because we want to distort it in anticipation of the loss of this channel. But the interplay between the electrical layer and the physical layer is really important here because we need these two things to happen basically at the same time. We need the physical transmitter to change on the system so that it's actually outputting the right type of signal, and we need the protocol confirmation back to the add-in card to say it's changed. So both of those things need to happen at the same time. So once the system has responded and said it has changed its cursors to the requested settings, the add-in card will take a look at the signal, which by the time it goes through this channel and gets to the add-in card receiver, it will be a fairly closed eye diagram here. Now the add-in card is going to tune its TXEQ settings to maximally open the eye. So you can see it can apply now some additional equalization on the receiver here to get an even better eye diagram. So the timing between these things is important because as soon as the add-in card sees the protocol response from the system that it changed its settings, it's going to start to tune its receiver equalizer. So if everything isn't synced up properly, then the tuning on the receiver side won't match up with what's going on the transmitter side. And ultimately, you can get this whole process failing to produce good results and ultimately end up with an unacceptable bit error rate. So after the add-in card has tuned its receiver here and it's happy with the result, it's going to send another request for different settings. So in this case, again, you can see another request from the add-in card for not a preset, but cursors to 17.5. So there's some different settings now. And then the system will respond back and say, okay, I have changed to 17.5. And at the same time, it'll physically change its TXEQ settings to apply these cursor values. And then again, the add-in card, once it sees this confirmation, is going to take a look at the signal it's receiving, and it's going to optimize its TXEQ settings to open the eye as much as possible. So it's going to continue to repeat this process a number of times, and how many iterations it goes through is implementation specific. So I've seen a lot of different types of products. Some just request a single preset, some request a variety of presets and cursor values, some request every possible cursor combination. So you can see quite a few different behaviors in the actual algorithm that chooses which presets or cursors to request from the system. But in any case, once it's made as many iterations as it's going to do, it will transition to phase 3. So we can see now, here we have a packet from the add-in card, and now if you look in the EQ control, you can see the phase has moved to phase 3. And at the same time, it's going to reflect the settings, the cursor settings in this case, that it wants the system to use for its transmit equalization from now on. So it's picked, these are the settings that we went through that whole process, these are the settings that I like best, I want you to use these settings from now on. It's also picked its own receiver equalizer settings as well, but it doesn't need to advertise those because that's set in the add-in card and not in the system. In phase 3 then, we have the reverse, where now we have the system requesting different transmit equalization settings from the add-in card, and the system is tuning its own receiver. So we'll see the same kind of behavior, just backwards. We'll have the root complex for the system here, requesting, in this case, it says use preset is yes, so requesting preset 1, and then we see some time later, add-in card responds and says, okay, I have changed to preset 1. And this will go through a number of iterations. and then we'll exit out of the recovery equalization state. So, we went through this long, pretty complicated process, and what did we accomplish? Well, in phase 2, we picked the optimal TXEQ setting for the system and RxEQ setting for the add-in card. And in phase 3, we picked the optimal TXEQ settings for the add-in card and RxEQ settings for the system. And those are both for that specific channel, right? If you plug that add-in card into a different system, it would come up with different settings. Even if you maybe change the temperature or you reseated the card, it may come up with different settings. I've seen a lot of devices that if you just run the process a few times, it may come up with some different settings. So this is definitely not a static thing. It's a dynamic, and it's configured every time you plug these two pieces together. But the end result, hopefully, is that we get a bit error rate of better than 10 to the minus 12. And this is going to ensure that we have a robust link where we're not going to have a lot of packet errors. We're not going to have a lot of retransmitting data. We're not going to retrain to a lower speed. And this is really also this is one of the requirements for compliance for PCI Express. So that was the overview of what is dynamic equalization. I'm going to go into, I've got to give you a little overview of the test equipment that we can use to make some measurements, and I have a lot of examples of different devices that had some problems or were misbehaving somehow, and identifying it and debugging it using this test equipment. So for compliance testing purposes, there's 3 different sections of electrical testing. You have the transmitter testing, which you can do on a scope. This is looking at things like jitter numbers, eye diagrams. We have receiver testing, which we can do with a bit error rate tester. We also need the scope for calibration. And this is just going to put the device into a loopback, and it's going to send in some calibrated signal with a bunch of jitter and noise on it, and we're going to run a bit error rate test. And then for the link equalization testing, which this is a required part of the compliance program, we actually need the scope. We need a protocol-enabled receiver tester, which is our PeRT3 Phoenix, and we need Protosync software, and I'll tell you a little bit more about what that is, because we're going to use these pieces a lot for the debug examples we're going to show. And I'll mention that equipment is really unique, the PeRT and Protosync, and for that reason, LeCroy is the only vendor that's approved to do all of the required electrical tests for PCI Express Gen 3. So there's no other system out there that can actually run these link equalization tests. So that's true for compliance, also on the debugging side as well. Okay, so this is the setup that we're using for pretty much all of these debug examples. This is also the setup that we use for the compliance testing as well. And it looks fairly complicated at first, but once we pick it apart, it's actually pretty simple. So on the left here, we have our PeRT Phoenix. Again, this is our protocol-enabled receiver tester. On the right, we have a scope. And then in the middle there on the bottom, we have our device under test, which is then plugged into some fixtures. So the PeRT can act like a PCI Express port, and it can act like either a system or an add-in card depending on what you're testing. So in this case, we're testing an add-in card, so our PeRT is going to be behaving like a system. And it's a system that we can configure and that we can control how it's controlling the add-in card. So we're using this as a system, but also a way to control the add-in card and to exercise this different functionality that we're trying to test. So in order to get the system to talk to the add-in card, we need to connect the transmitter from the PeRT to the receiver on the add-in card and the transmitter from the add-in card to the receiver on the PeRT. But we're also going to insert these splitters into both sides here. Both the upstream and downstream links, we're inserting these splitters, and we're picking off the signal and sending it to the scope. Now we have the capability to monitor the upstream and downstream traffic at any point during the whole link training sequence, and we can view the waveforms on the scope. Now the memory on the scope is fairly limited, right? We can only capture maybe you know, a millisecond or a couple milliseconds at the most, but usually a couple microseconds. So what we do is we feed a trigger from the PeRT to the aux-in on the scope so that we can trigger the scope at a specific point where we want to be able to view the data. So we capture just what we're looking for. We don't have to capture the entire link training sequence. And then in this case, we're testing an add-in card, so we need to supply a clock also from the PeRT. So we have a clock out from the PeRT into the add-in card. So we're going to use this PeRT to exercise the add-in card, and then we're going to pick off the signal and look at it on the scope. So what I'm showing here on the left, all this text, this is a state machine log from the PeRT. So as the PeRT walks the device under test through the different states, it logs each of the states it goes into, so you can, as a user, you can view each of the states and you can see exactly where your device is going and where the PeRT is taking it. So if you remember how I showed you on the LTSSM plots how to get into recovery.equalization, you can see that the PeRT is doing exactly that. So you can follow these state names here. We're going from detect to polling, config, L0, recovery, and then we can see recovery, receiver lock, receiver config, speed, and then back over here to receiver equalization. And then even inside of the receiver equalization, if you remember I mentioned there's these 4 phases. You can see phase 0, 1, 2, and 3. So we're able to actually see exactly into the protocol where we are and where the device is and what's going on. I should also mention we can actually set the trigger out from the PeRT at any one of these states in here, or a number of the states in here. So if you wanted to be able to view exactly what your device is doing, you can set a trigger out, for example, in recovery.equalization phase 2, and you can capture on the oscilloscope exactly what your device is doing in phase 2. And that's what we're showing here. So we acquired some waveforms on the scope, but we can display them not just in the scope, but using our Protosync tool, we can display them also in the protocol analyzer software. So now we have side by side the electrical waveforms and the protocol view, and that's really what we need, because all the communication is going on the protocol level, but there's a lot of stuff also happening in terms of the equalization settings being changed. That's really all taking place in the physical layer. So we need to have both views simultaneously, and that's what Protosync allows us to do. And actually with Protosync, you can click on a packet in the protocol view, and it's hyperlinked back to the electrical view, so it'll zoom to that location in the electrical waveform of that packet from the protocol view. So we can identify something like, for example, a preset request in phase 3. We can click on that, and we can see exactly where the request was sent in the electrical waveform. Okay, I'm going to jump into some of the examples I have here. So what I'm showing here is these are all basically the setup that I just described. So in this case, we have a protocol view up here, and we have the electrical view here, and we have the system is sending a packet, and we're in phase 3. So this is where the system is adjusting the add-in card's transmitter equalization. So the system in phase 3 sends a preset request of preset 1. So it's saying, I want you to change your equalization settings to preset 1. And if we click on this in the protocol view, it creates a zoom, which we can see as the pink trace, in the yellow trace, in the exact time location where that request was sent. So we can see right here, this is where the request for preset 1 is sent. And then we can see the actual electrical change over here changing to preset 1. So I think this is preset 7 here, and you can physically see the amplitude changing in the waveform. And what you see with this particular example is the request was sent here, the physical change happened here. We measure the time delay, and the time delay is almost 6 microseconds. And the requirement in the base spec is 500 nanoseconds or less, and for the compliance test requirements, it's 1 microsecond or less. So this device is taking way too long in order to actually change its equalization settings after the request. So this would cause a problem in a real system, because during this time here, the add-in card or the system thinks that the add-in card has changed its equalization settings, and so it's trying to tune its receiver here. We're tuning the RXEQ, and then all of a sudden it actually changes the signal it sees. So I'm not sure actually what the answer it would come up with, but this would definitely have an impact on the RXEQ tuning algorithm of the system. This would also fail the compliance LinkEQ compliance test for the electrical response time. But this is a really interesting test here, because we're looking at a request sent in the protocol, and we're measuring that compared to a response in the electrical waveform. So this is a really unique test, and that's why you need the protocol-enabled PeRT and the Protosync capability in order to be able to make this measurement. This is an example of the same test, the protocol electrical response time. And in this case, you can see a different behavior with this device. We have the root complex, which is actually the PeRT in this case, sending a request for preset 1 again. And you see the add-in card is responding and saying, okay, I changed my TXEQ to preset 1. But when you look at the electrical waveform, it never actually changes. So just because it's giving the response in the protocol doesn't mean the electrical TXEQ settings ever change. In this case, you can see it didn't really change. For the protocol, this would not be this problem would not be caught in a protocol test, because it's just an electrical problem. Here's the same test here, the response time test. We're looking now at, again, the PeRT, which is the acting as the system, sent a request in this case for preset 4, and we can see the add-in card responding, saying, okay, I've changed to preset 4. But if you look at the time delay, 9.7 microseconds. So in this case, the protocol response is too slow. Actually, with this product, the electrical response was less than 1 microsecond, but the protocol response came almost 10 microseconds later. So there's a few different ways to go wrong with the protocol response, and that would be either no electrical response is too slow, or the protocol response is too slow. So you need to get both levels of that correct. Here's an example where we sent, if you look at the state machine log from the PeRT, you can see recovery.equalization phase 2. So in phase 2, the add-in card is requesting a preset, it requests another preset, so it goes through, I think, all of the different presets here. Transitions to phase 3. In phase 3, the system sends a preset request. It waits for the reply, doesn't hear anything back, times out. So what we can do is go to our PeRT options, and we can set a trigger for EQ timeout. So when we hit this timeout right here, it's going to send a trigger to the scope, and we can capture the waveforms of the upstream and downstream, and we can see exactly what's going on at this point. And this is exactly that. We've acquired the waveforms on the scope, and if you look at the protocol trace, you see what we saw from the PeRT state machine log. We can see a preset request, preset 4 from the system, and then nothing. And if you look at the electrical waveform here, you can see again this is the preset request in pink, and then all of a sudden it looks like it goes to electrical idle. With this particular case, actually when we zoomed in on this waveform here, which looks like electrical idle, we could actually see the signal, and it was at 20 millivolts amplitude. So what we saw was other presets, like preset 7, didn't have this problem, but preset 4, it shrunk down to 20 millivolts amplitude. So this was a bug in the firmware, I think a typo, where somebody had, when preset 4 was set, the amplitude was reduced to 20 millivolts. So this was a bug that we were able to identify using this debug approach. Here's another example where we have, again, we've requested a specific preset from the device under test using our PeRT. And when we get that response, what we actually do is we acquire that signal on the scope, and then we save the waveform. And so we go through and we actually request every different preset, and we save each of the responses. And we want to test to see if the electrical response is actually the preset we asked for. And in this case, you can see we're checking each of the waveforms here, and all of them pass except for P8. So preset 8, when we requested that, the response should have been 3.5 dB pre-shoot and 3.5 dB, minus 3.5 dB de-emphasis. But in fact, you can see it's almost 6 and minus 6, so off by quite a bit here. So this is not the correct electrical response. Here's another example showing bit error rate measurements. So when you run through this recovery process, at the end of it, your device should have picked a transmit equalization setting that it wants its partner to use. Now, it can only pick one setting, but when we're testing things, we can test a whole variety of settings. So in some cases, it picks a setting, we run a bit error rate test, and it doesn't get the required 10 to the minus 12 bit error rate, even with the setting it picked. So in this case, we ran a number of bit error rate measurements, sweeping different de-emphasis and pre-shoot levels. So on the bottom here, we have different de-emphasis amplitudes, and then the color codes are different pre-shoots. So we swept a large combination of different possible pairs of de-emphasis and pre-shoots. And what we see here is that no matter what settings are picked, this product cannot get better than 10 to the minus 8 bit error rate. So there's just no way, even if that algorithm is tuned perfectly, that this device is going to be able to get the required 10 to the minus 12 bit error rate. And this is going to cause a lot of problems if you try to use this in a real system. And this certainly would not pass the compliance test. So I have even more examples, but I wanted to leave some time for questions. So I'm going to wrap it up at this point. Again, I focused a lot on the recovery state here, and it's these three pieces of equipment that we offer from LeCroy that really allow you to look into that recovery state, look into that dynamic equalization process, and understand how your device is behaving in there, and also do the required compliance test, but really to understand and debug a lot of the problems in there. All right, I'll open it up for any questions. Thanks, everyone, for your attention and for joining us today.
Thank you, Stephen. Thanks, everyone, for joining us today. I see a few hands up. Please note that I need you to type in on the chat panel the question, unless you want me to take you off mute, which I could do that as well. So a couple questions. The first one is the presentation recorded? The presentation is recorded, or is being recorded, I should say, and the slide deck is available, and I will send out a URL for both of those after this event. So thank you for that question. The second question, how to detect what is the cause of the device if the device is getting locked in a particular state?
Okay, yeah, good question. So come back up to here. So this is really the way to do it. So a lot of times what you'll see is this, let me go back, this is the whole connection log. If your device works really well and you run the test with the PeRT, you should see this in the connection log. So it starts off at, detect.quiet, goes through the whole link initialization, goes through recovery. We finally go into loopback, and this is where we can run any bit error rate tests in loopback.active. But if your device gets stuck somewhere, well, if you don't have the right test equipment, you're just stuck. You have no idea what's going on there. With this setup, it really gives you a really powerful debug tool, which is you can set a trigger then, which I show in this example here. So now we're setting a trigger on that specific state where it got stuck. So this is EQ timeout, but you could set it other places as well. There's a whole variety of different trigger settings. Like one that's pretty common that I use a lot is loopback.active. Some devices will, or loopback entry, some devices will just get stuck at loopback entry and not actually go into loopback. Or they might get stuck like we saw here in phase 3. So you set the trigger there, then you use the scope with the splitters to acquire the upstream and downstream traffic when you get to there. Then you can use the protocol and the electrical view to figure out exactly what's going on with the signal in both of those layers.
Okay, so Shank, hopefully that answers your question. If not, please let me know. The next one is from Robert. He wants to know how you can take PeRT measurements on embedded devices, both root, ports, and endpoints.
Yeah, so that's pretty difficult. So most of what I talked about here was really about PCI Express devices with connectors on them. And that makes things easier from a test standpoint because you plug the connector into a fixture and then you have these nice coaxial connectors, which are like SMP connectors on the board. And then we can hook those into all the coaxial connectors on our test equipment. If it's an embedded system where you just have some chips on a board and some lanes and stuff like that, it makes it harder from a test standpoint, but it's easier. It's easier in general because what you can do is just you can tune those equalizers for that specific system, and then you don't have to use any of this dynamic equalization stuff because the channel looks the same every time you power it on. Right? You're never going to break the board in half and then connect 2 different boards. It's always the same. So you can figure out the settings that work the best. You can fix those and you can bypass recovery every time you boot up. So it's probably not necessary to do this kind of dynamic equalization testing. You may want to do receiver testing, which you can do. You'd have to create basically a test board that had connectors on it. There's no way to use probes, for example, with the PeRT.
Okay. Robert, if that doesn't answer your question or you'd like to discuss this in more detail with Stephen, I can certainly set that up, so just let me know. The next question is coming from George. He wants to be taken off mute to ask you. So, George, you're off.
Okay, thank you. Question is, when it goes through the equalization process, does the receiving end in the receiving device actually first goes for a bunch of transmit settings for its partner, and then it chooses one and then does receiver equalization, or it does one transmit equalization, then a bunch of receiver equalizations, then tries the next transmit thing from its partner and does a bunch of receiver? I mean, how's the order of those things? And also, what is the choice between it choosing doing presets or cursors? Is it does first they do first presets and then they do cursors to fine-tune, interpolate between 2 presets as the optimal setting, or I just don't understand the whole methodology.
Okay, yeah, sure. Let me clarify that a little. So what we have basically is initially we have the add-in card goes first, and it's going to adjust the TXEQ of the system and its own RXEQ. So what it does is it sends a request, and it says set your TXEQ to something, and it can be a cursor or a preset. Once the system responds back and says, okay, I've set those settings you requested, then the add-in card will adjust its receive equalizer. And it'll go through, it has its own algorithm internally that'll go through a bunch of options, and it'll figure out which one it likes the best. Then it's going to request another TXEQ setting, adjust its receiver. Request another TXEQ, adjust its receiver. Then finally they switch, and in phase 3 the system gets to adjust the add-in card's TXEQ and its own RXEQ. So the add-in card goes first, then the system, and they kind of go through a bunch of options. In terms of the presets versus cursors, that's totally implementation specific. You don't have to go through all the presets and all the cursors. It's totally up to the implementer how many cursors or how many presets, or if they want to do just presets or just cursors. That's left up completely to the implementer on how they want to do that.
Okay. Also, an equalization process, is that only done power up, or is done dynamically as the bear? They keep tracks of the bear dynamically, and if the bear becomes unacceptable, then it starts a new sequence as for a warm-up, for example, as the equipment warms up.
Yeah, good question. The question is it done? Is the recovery equalization done only on power up, or is it done throughout the system? So it's done always on power up, but then it can if a lot of bit errors are detected, it can retrain at any time. So if you bump into it and something happens, or if the temperature changes or anything, it can always go back through recovery and redo all of this optimization. And also, if it goes through a couple times and can't actually find settings that work, it can retrain to a lower speed and just go down to 5 gig.
Okay, excellent.
So it always happens on power up, but then it can happen also later on.
So the later on is actually implementation dependent. It's voluntary per the device maker.
I don't think it is. I think there's always some chance to retrain depending on how many packets are lost and that kind of thing.
Okay.
I'm not sure on that thing.
Yeah. Okay. Excellent, Stephen.
All right.
I'm going to put you back on mute. If you have any other questions, just email us, okay?
Okay, sure.
Okay, thank you. All right, so we have a few more questions. One is, can Python scripts for Gen 3 auto test be purchased?
So yeah, we've created a set of Python scripts that automate all the link equalization tests. So we talked about a couple of them today, which would be like the response time test, and also making sure that the response is the correct response electrically. So there's a number of these link equalization tests, which I didn't focus on today. I think we have another webinar that's posted on the website that focuses more on that. But we have scripts that run all this stuff that control the PeRT and Protosync and the scope to actually execute those tests. So we give those out for free with the equipment. Those are not for purchase. That's just a free tool we give out.
All right. So.
But if you have the equipment and you don't have those scripts, definitely contact me and I can send it over to you right away. Plus a whole bunch of other documentation and things if you don't have that already.
Yes, I just emailed you. There's not a complete first name, but Mr. Lee, my email address. And so you can email me and I'll put you in touch with Stephen. All right, so the next question is from Bharat. My question is the amount of de-emphasis and pre-shoot has as per preset settings. Can't this be different depending upon impulse responsive channel?
The preset, they are what they are, but the preset that you pick is going to depend on the channel, right? So these are the different presets here listed. This is, all these images are right out of the spec. But, for example, P0 is 0 dB pre-shoot and -6 plus or minus 1.5 dB de-emphasis. So that's what preset 0 always is. Now, the question is, do you want to use preset 0, or do you want to use preset 7, or do you want to use preset 4? And that's going to depend on the receiver on the other side, and it's going to depend on what that channel looks like, right? So if you have a really short channel, you might use P4, which is 0 dB and 0 dB. If you have a really long channel that has a lot of loss, you might be looking more like using P7, which is 3.5 dB and -6 dB. So, how you choose the preset or how your device chooses the preset definitely depends a lot on the response of the channel and on the receiver equalizer on the other side.
Okay, Bharat, if that does not answer your question, please let me know, and we'll take it either additionally here or offline. The next question is from Tariq. How many equalization setting iterations does the system and add-in card go through to optimize the channel?
So it could be, the maximum would be every single possible combination. So there's devices out there that do every possible cursor combination, and that might be like 42 different iterations. And then the minimum is 1. So some devices just hard code a setting. Especially like you'll see that sometimes with like servers or something like that. They'll just hard code it, so it'll just be, they want P7 every time. And I see that some cases that's done because the receiver equalizer for that device is really good. Maybe they have a 5-tap DFE or something that can really handle almost any signal it can get. In other cases, it's done just, I think, because it's cheaper or less effort. And then in a lot of those cases, you see that it doesn't work out. They can't pass these tests by just hard coding the preset. So the minimum is 1. The maximum is, every combination. So like, might be up to like 42.
Okay, Tariq, hopefully that answers. If not, let me know. The next question is from Shashank again. In one of the states, we need to wait for, he was the one who asked the first question about detecting what is the cause if the device is getting locked in particular. Okay. So in one of the states, we need to wait for idle symbols. Can you highlight if the setup can detect idle symbols?
So I'm not sure I understand the question correctly. So yeah, I'm not sure I understand that one. Maybe you could send an email with a little bit more detail.
All right. I will send you Stephen's email so that you can ask the rest. Okay, so I think that is it. Someone again asked if they can watch the webinar at a later date, and the answer is, oh, it's IDLE symbols. Is that different than?
Yeah, I'm just not sure what state or why they'd be waiting or something like that.
Okay. So the webinar is recorded. You can access it using the URL that you logged on today with. But in addition, I will send out a follow-up email in a couple of hours once it's had time to record itself in archive. And I will also include a URL to the slide deck. So if anyone has any other questions, you can reply back to my email, and I'll get you in touch with Stephen or your local sales engineer. And we just want to thank you again real quick. We only went over by 3 minutes, so that's not bad. But we appreciate all your questions and your time. So,
all right, thanks everyone.